So let us start today's session, which is going to be on CNN and different types of available CNN architectures. So let's small amount of recap which is being required, and then we and three more small things. First we will talk, and then we will go to see in detail few CNN things and the different case studies. So and also several of you were in the last lecture trying to ask that there are so many hyperparameters are there. Parameters, so there are two things we have talked about. One was parameters and the other one was the hyperparameters. So it's parameter and hyperparameter. So hyperparameters, we need to fix it up. This is going to be learned by the system. So there are huge number of parameters. Hyperparameters are also too much, like how many layers, how many layers, and whether your filter is actually 3 by 3 or 5 by 5, or what type of filters you are looking for. So, and um, how many filters in a layer. So these are actually the hyperparameters. So given this thing, let us give you a very brief overview in which, suppose that I have an image, this image can, so right now we are talking about CNN. When we talk about CNN, it has to be a 2D matrix or an image, over which we used to apply this thing, because we here are actually applying two-dimensional filters, so it has to be applied over 2D type of data. So suppose that if I have image like this, in which we are having, say, 28 by 28 is our input dimension, and this is going to be there. Suppose that, yes. So suppose that I'm having my first layer. This is my, say, layer number 1, and then I may have layer number 2, and then probably I'm having multiple layers, and at some point of time I have flattened it, and then I have got a fully connected network, which is something like this. Last layer is going to be the amount of classes that we are having. If I'm having 4 classes, then last layer is having 4 neurons. So what I try to say over here is that every layer is going to say that, tell me that what is the size of filter that you are looking for. I'm saying 3 by 3, suppose that. So it may be 3 by 3 or 5 by 5 or whatever. Something one should have to choose. And then you will have to tell that how many filters of such type. I am saying that, suppose that I am looking for initial layers, I am looking for only maybe 32 filters. Then here I apply 3 by 3 filters, and how many? 62, 64, and then probably I again apply some 3 by 3 filters. And how many such filters? Again, I apply, say, 128 such filters, and keep on doing. And at some point of time, I open it. So soon we are going to see that. Anyways, we have talked about these filters and number of filters. I will show it in detail in upcoming slide. So this is going to be a general architecture in which, why we are coming up with the 2D filters. We have talked about this 2D convolution and 2D filtering, and it was just because of the fact that we are interested that this pixel is having some relationship with this, and this pixel is having a relationship with this, or this pixel is actually having a relationship with the neighborhood, which is actually being somehow utilized. And how we can utilize, if I want to know something about a pixel, I need to ask within a neighborhood. So this is a way by which we can ask something about this pixel within a particular neighborhood. So that's actually 2D convolutions that we have seen in our previous lectures. The only thing is that 3 by 3 essentially mean that what is the scale at which I wanted to ask, what is the neighborhood to which we are actually looking for, and this is going to tell that how many filters I am going to apply. So number of filters, if I apply 3 filters, then you are going to get 3 outputs. If I apply 32 filter, then we are going to have 32 outputs. So this layer is going to give me 32 outputs. This layer is going to give me 64 outputs. And suppose that here there is some layer that's going to give me 128 outputs. So in between, we have also talked about that we will be doing the max pooling. If I do max pooling, then size becomes half. Then if I do again max pooling, and after certain amount of time, you will see that the output dimension. So this is actually the different output that I am going to get. So I am going to get 128 such outputs, and each of them may be of very small size, because initially it was 28 by 28. Maybe after a few max pooling, it become 4 by 4, and you are going to get, this is your output dimension, which is saying that I am having 2 cross 2, and how many such things? 128 such things. So then you flatten it, and then after flattening, you can apply fully connected network. So this was the thing that we have seen previously. Two more things that we want, and maybe at right now, so I wait, and maybe I will talk about this when I reach there. So yes, so we are going to start from here. So we have seen in our previous lecture about our convolutional neural networks. So what we are going to see today is that, suppose that if I have an image of size 32 by 32, and this 32 by 32 is the input dimension, and obviously this 3 is going to be the, because your image is actually RGB image. Usually if you see that your RGB image, you have a R channel, you have a G channel, you have a B channel. Suppose that this is 32 by 32, then this is also 32 by 32, and this is also 32 by 32. So your dimensions, this is actually going to be 32 by 32 by 3. That is your input dimension. And 3 is actually the depth, RGB depth that you are actually looking for. So here you can see that this is my 32 by 32, and this is actually the depth that I am talking about. So paper view, single page, yes. So yes, so now if I say that over this, if I wanted to apply a 5 by 5 by 3 filter, so what does it mean? That if I wanted to apply a 5 by 5 by 3 filter over that, first of all, let us understand that if it is going to be a 5 by 5 filter, then suppose that at any point I wanted to apply, suppose that at this point I wanted to apply, then it is going to take a 5 by 5 patch around this pixel. And how many things are going to be there? So there are actually 5 by 5, 25 things which are being here. And this is actually a filter. So this filter is actually having 5 by 5 by 3. So it is having a Rubik cube type structure. This is actually a kernel. This is actually my filter, which is having 5 and 5 and 3 such things. And when this filter I take it and place it over here, what it is going to do is that its first phase is actually for R, the second phase may be for G, and the third phase is actually for B. So what will happen is that this is going to have 5 by 5 by 3. That's actually 75 things, out of which 25 is actually for R, 25 are for G, and 24 are actually for B. So I take this filter, place it over here, and what you are going to do? You are going to do this 75 multiplications. 75 multiplications. If you do the 75 multiplication and add all of them, you are going to get a single value. That single value is actually the output of this filter for this pixel. Please, I mean, if you are able to understand, then it is fine. Otherwise, you can ask in between, because I guess it requires some understanding. Is this okay to everyone? Hey, do we have anyone? Yes, please ask. I get
Can you explain one more time?
Yes, I explain one more time. So the point here is that wait. Yes. So let us see that what we are doing over here is that this is my 32, this is my 32, and this is my 3. So this is my input given to me. And what I wanted to do is that I have a 5 by 5 by 3 filter. This 5 by 5 by 3 filter can actually be seen as 5 by 5, the second 5 by 5, and the third 5 by 5. This is my 5 by 5, and this is these 5 by 5, 25 values are actually for R channel, and this is for G channel, and this is for B channel. So you are actually getting a volume, Rubik cube type volume. If you just think about Rubik cube, that's a 3 by 3 by 3. It is 5 by 5 by 3. I take this thing, and if I wanted to know something about this pixel, I have to place this Rubik cube over here. So if I place my first Rubik cube's first face over here, then the second face will actually be here, and the third face will actually be here. And what will happen that here you are having 25 image value, here you are having 25 image value, here you are having 25 image value, and the corresponding kernel values are here, 25 kernel values here, 25 kernel values here, and 25 kernel values here. Now you take this value and multiply with them, you are going to do 75 point by point multiplication. That's actually the convolution that we have seen. In convolution, what we used to do, if I have an image, if I have a kernel, I take this, for this pixel, I place my kernel over that, and this value got multiplied with the corresponding image values. These values got multiplied with the corresponding image value. Here it's only a 3 by 3. Suppose that it's actually a 5 by 5. So if it's a 5 by 5, then it's going to be a bigger size kernel, and 25 multiplications you are going to do. Same thing is actually happening over here. Instead of 5 by 5, I'm having a 5 by 5 by 3 kernel. And this 5 by 5 by 3 kernel is actually 5 by 5 by 3 in this way. So I take and multiply and find out a single value for this guy. So if I get for this guy, then I stride it into my X direction as well as in the Y direction. It will be moved. So for this pixel, then for this pixel, then for this pixel, then for this, and so on. Once you are done with this, then you go down and then you do it in this way. Then you do it in this way. So that is actually the raster scanning that we have seen. So how you are going to compute it is that first you find out them. Once you are done with this, then you go and then you do this, and then you find out for them. So this is actually moving in this direction continuously, and then you are moving in the Y direction. So first you move in X, then you move in Y, and you are done. You have got for each pixel here, each pixel you have got a corresponding output. So if I have a filter like this applied over this, you are going to get an output like this. Is this okay?
Yeah, it's
fine. This is okay. Yes.
Aditya sir?
Yes.
So we'll be getting only one values corresponding to RGB. Only one.
Yes. Yeah, that is the most important thing. Yes.
Okay.
Yeah.
Okay. So we'll be doing 75 calculation. We'll get only one value.
Yes.
Okay.
So that is actually and this one value is corresponding to a particular specific X, Y location in my image.
Okay. Okay.
And that is the meaning. That is the meaning that actually whatever is here, it is not only governed by R, its red value, it is actually being governed by its R, G, and B, all of them.
Okay. Okay.
Because of that, instead of asking just to one channel, we are asking to multiple, or in fact, all of the channels.
Okay. Okay.
This is okay?
Okay. Thank
okay. Then there is another thing that this is actually a 2D convolution. Why it's a 2D convolution? This is actually a 2D convolution. Just see that our filter is actually 5 by 5 by 3, but still it's being called as a 2D convolution. And the reason is that because it's a 3D filter, it's a volume type of filter, still it is 2D. Why? It is 2D because you can move your filter either in this direction or in this direction, either in X or in Y. So because of which, and why you cannot move in your third dimension, that is actually 3 here, is that this 3 and this 3, they are same. This is called that your, this is called as that your depth of your filter and the depth of your input is actually matched. This is called as fixed. And you fit, this is called fit. So your filter is actually fit to your input. So that is why it cannot move in the depth. It can only move in X and move in Y. And that is why it is called as, because there are only 2 directions in which you can move. That is why it is 2D filter. Even though it's actually a 3D filter, convolution is actually called as 2D convolution. Is this okay again? This is fine?
Yes, sir.
Okay.
Yes.
Yeah, this is okay. So yeah, so there's 75 multiplications. You have got a single thing. And one thing that you again wanted to ask is that if all this stuff is here, then something is going to happen. That suppose that if I have an image like this and I wanted to apply and my let's say my filters are, my pixels are like this, and I wanted to apply a 5x5 filter over here. So you cannot apply a 5x5 filter over here because it is not having its all possible neighbors. You first filter, first pixel over which you can apply your 5x5 neighborhood is actually this, because this is having 2 pixels up, 2 pixels down, 2 pixels left, and 2 pixels right. That is actually 5x5 neighborhood. So what will happen is that this is the first pixel and this is the area in which you are going to do your multiplications to find out your value for this pixel. But you cannot do it for this guy. You cannot do it for these pixels, and these are boundary pixels. You cannot find out the information. And the reason behind is that they do not have their full or all bound neighborhoods. So in this way, one way is that's being done is that either you do padding. So if I do 0 padding, and how much? 2 row up, 2 row down, 2 row bottom, and 2 row ups. So in this way, what we can have is, this is actually called as 0 padding. It's a simple image processing concept in which we used to do this thing. So now you can see that even this pixel is having all of its neighborhood, to this, to here, and to down. So now with this, you can find out the information with respect to this. So either we do 0 padding, or we ignore the boundary pixels, because that's only 2 pixels that you are not able to get. So 2 boundary pixels, so 2 row, 2 bottom rows, 2 up row, 2 left columns, and 2 right columns. You will not be able to get the information. So because of that, in this example, what they are doing is that, suppose that if I apply a filter of 32 by 32 and 32 by 32 by 3, 5 by 5 by 3, this is anyways going to happen. And that is actually the convolution we just have talked. There's a 75 multiplications which are going to happen, and this is going to be multiplied, and you are going to get a single value, and then you move it in this direction and this direction to find out for each and every one. You are going to get a 28 by 28. Now I guess that you can understand that from this point to this, from this point and to this, you are applying. You will not be able to apply your filter here because they are not having their each and every neighborhood, possible neighborhood. And because of that, as I have said, that because it's a 5x5 filter, which means that 5x5 filter means that, like it's actually like this. So this is my center pixel, 2 pixel up, 2 pixel down, 2 pixel left, and 2 pixel right, which means that 2 pixel up, 2 pixel down, 2 left, and 2 right, you will not be able to get. So essentially from 32, the things are actually going to be 28 by 28, because 32, so 2 and minus 2, so that's 28, because 2 up and 2 down. So that is the width for which you can get your data responses. And same you are going to do for 32, 2 left row, 2 left column, and 2 right column. So these things are actually not able to give you information. In this case, either you do zero padding. They have not done the zero padding just for this example. So now you can see that you are getting 28 by 28 and only one such depth. Depth is actually one. Why? Because it's actually a fit filter, and you can see that once you take a filter, apply it over the whole image, you are going to get a surface like this. For every pixel you have got the information, and how many information for every pixel? Only got one such thing. So suppose that if I apply another filter, same another filter 5 by 5 by 3, if I apply another filter, so this was my response for my first filter, filter number 1, and that's a response for my filter number 2. So I have got filter number 1, I've got a filter number 2, so I've got two responses if I apply two such filters, and both of them are going to be 28 by 28. So suppose that if I apply 28 by 28, so here it's actually that I have applied 5 by 5 by 3 filters, and how many such? I have applied 6 such filters. So I have got a response map of 28 by 28 by 6. So that's my activation map, so the response map that I have got, over which I am going to apply my upcoming filters. So that's my input, that is my one layer, layer number 1, and then I have got an output. Output is actually 28 by 28 by and 6. So now suppose that, yes.
At point of time, do we know how many filters to use, like 3 or 6 filters, like?
Yes, so usually I'm going to talk about them because this is something being done very frequently, and one should have to understand huge amount of stuff by how they have designed these networks. So we are going to see few available benchmarking very good and well performing networks, and from there we can understand that when to use and how to use and what type of filters and how many such filters. So that is the designing part.
Sure. Thank
you. Yes, so suppose that with this, so here I have applied, as I have written, 5 by 5 by 3 and 6 such filters. I have got 28 by 28 by 6, and suppose that over that again I apply say 10 filters, and if I again apply 5 by 5 filters over this, you can apply, but this time it has to be 6. It's not going to be 5 by 5 by 3, because this 3 and this 3 has to match, and this 6 and this 6 has to match. That's why it's 5 by 5 by 6 filters we have applied. When you code, then if you write that my input is this, and in your output, if you have only written 5 by 5, you just have to write 5 by 5. You need not to even write 6, because it understands that it's a 2D filtering and this has to match with this. So this 6 and this 6 is anyways going to be matched. It's not being written even in the code. It's understood that it's a 5 by 5 filter, which means that a 5 by 5 by 6 filter is there. So if I apply a 5 by 5 by 6 filter, you are going to get one output, that's of 24 by 24. Again 4 got reduced. So from this 4 got reduced, 28 to 24 you have gone. So you have got 24 by 24, one such surface. And how many such surfaces? 10 such surfaces we are going to get. 10 such outputs and activation maps, if I say, you are going to get when you apply 10 such filters. Yes, so this is some visualization. Maybe we can come at some point of time. But yes, so here what they want to show is that suppose that this is my input, and these are actually my filters. These my filters. So there are 5 by 5 and 32 such filters, 5 cross 5 filters, and how many? 32 such filters. If I take these filters one by one and place and convolve this image with all these filters one by one. So if I take this filter, convolve here, you are going to get an output like this, which is being shown over here. If I take the second one, convolve here, you are going to get an output like this over here. So these are actually the outputs that are going to be seen. What they wanted to show it over here is that, suppose that you just check it out, this type of response. response. This is actually just trying to say that this filter is trying to look for a response, which is saying that is there any red blob type of structure being present? A red blob type of structure. Only those pixels which are capable to say that yes, I have something which is very, very close to this red blob type of thing, then they are only going to be high. So that's actually being shown over here, that here you can see in this you can easily see that this is the region. Can you see this pointer, red pointer, which is now coming? Red
Yes,
pointer?
yes.
Okay, fine. So that's why I need not to write. So yeah, so this red pointer is actually telling you that if I take this image and apply this filter over this, then you are going to get something like this. So which essentially says that yes, this area in the image is actually saying that yes, this type of filters response is high. So now you can see that these filters are probably trying to learn about some car representation, and this filter was typically looking for, suppose that the backlight, and backlight was here, so that's why it got high. This area is actually get high and other things are not got high. So what is this area is actually when I take this filter response like this, and this area is actually high, responding to the point that yes, I have got something which is very close to the filter that's being
Last
shown.
last 1 minute, 1.5 minutes, we were not able to hear your voice.
Oh,
That
not hear you.
but,
Okay, I will explain it again. What I was trying to say here is that just look for this filter, and these are actually the filters that we have. Suppose that a network is being trained. After training, and it's being trained to detect a car, whether there is a car or not. It's an example, by the way. So it's trying to say that I am having a 5 by 5 filters and 32 such filters. So these are 32 filters. Filter number 1, filter number 2, filter number 3, and so on. This is my input image. If I take my input image and convolve it with my filter number 1, you are going to get this. This filter number 2, you are getting this. Filter number 3. So if you take any filter and convolve it with the image, you are going to get some activation maps which are being shown over here. What they wanted to show is that this specific filter is actually trying to learn that whether there is something which is very good, very high orange thing. It's trying to learn this thing, that only those pixels are going to respond to this type. Respond means that when you take this type of filter and place it over any pixel, and if it is having something which is very orange, then it is going to give you the high value. Only those pixels are going to give you the high value, which can actually be seen over here, that now you can see that here this part is actually high, and the reason is that this was actually having a backlight. So this was that this filter somehow learned that if there is a car, then can be a backlight, which is most of the time very similar to some orange type of color. Is this okay?
Yes, got it.
Yes. So that's the only point that wanted to show, that these filters are trying to learn something which is very unique, maybe related to the images over which you are working, and trying to learn something very interesting and useful structures which are there in the image. Everything is actually, every filter is learning something, and these are the input images. All of them are actually different input images. All of them are different input images seen by these filters. So filters are looking images in this way. Filters are looking the same image, and this is the representation of this image itself, but via different filters. So now you see that why you want more and more filters, because you want more and more eyes, because you want more and more perspectives, you want more and more visual questions that you are asking to the image. So different visual questions are being asked in order to do different visual cognitive tasks. Our task was, suppose that whether there is a car or not. So this filter actually has learned to see this image in such a way so that if there is something which is very orange, can be lit up. Maybe others are learning the shape, structure. something which is non-trivial, which is being there, and which is there because there is some car type of structure. So that's actually the activation maps and image. So single image you can see, if I say it in a very different language, or one can say the mathematical language, this is actually that the single image is actually being transformed or projected into another set of images which are very useful to somehow do different types of classification tasks in which you are looking for. So if you have a car, then this filter is high. If you have a cat, then this filter will not be high. Some other filter will be high, which is responsible to somehow say that whether there is a car or a cat. So filters are being learned in such a way. So so they have also shown that you do conv, then ReLU, then pools, and then conv, ReLU, pools, and so on. And this is our final last layer, which is going to say that after doing all that stuff, given this car as an input, you are going to get the final layer, which is saying that it's actually a car with a high probability. So last layer is actually simple neurons. We have talked about this fully connected thing, and it's going to be 3 to 5. Only 5 classes are there, and first is actually for the car, second one is for the truck. So how, with what probability it's actually a car or a truck or a plane or a ship or a horse. This is also done, and I guess that the same thing is actually trying to say that here you can see that first you take this and then it keep on moving. We have already covered this stuff, so I'm skipping. We have that's a stride is going to talk about. So slides from some CS231 slides from Stanford University. So they have explained it very well. So now they are talking about that if you wanted to find out full information for the image, because if it's actually a 3x3 filter, then everything is not being computed. So we used to do the zero padding. So if you do zero padding, then the output after convolution remains to be of the same size. Then they have also given some nice formulas and some in between things. We are anyways going to skip because we have understood all that stuff. And this is actually the formula that they have given very easily. We all can understand that if your input dimensions are this and your filter is, if you apply K filters of size F cross F and the stride is S, then what is going to be the output? So I guess that is not of our use much. We just have to understand that this thing is actually working. Now we are going to talk about few very simple case studies, and then now you can understand that how to design such networks. And yes, you can easily say that why you require 6 filters. Sometimes you require 3x3 filters, sometimes you require 5x5. So soon you are going to see that not now. This actually started in 1998, and they started to come up with different types of networks in the last say 20 years, 20-25 years. They have actually designed and understand that what is the best possible design practices. And to understand those design practices, we are going to see multiple different types of case studies. So let's start one by one about them. So this is actually 1998 LeanNet architecture, in which the input was 32x32, and then they have applied 5x5 convolution. That's a 5x5 convolution, and you have got and how many such things? Six filters. So first layer is actually input was actually say 32 cross 32, and then you apply 5x5, and how many such things? 6 such things. So that's why you have got 28x28x4. I guess this is okay. 28x28x6. And once you have got this 28x28, then you have done the max pool. So if you do the max pooling, then you are going to get 14x14. Remember that max pool can reduce your spatial dimensions, because out of 4 you are going to choose the one which is maximum. So that is why it becomes the single value. So it's actually become 4 to 1. If it becomes 4 to 1, then your height and width is got reduced by half. And then we apply again convolution. So over 14 by 14 cross 6, if I apply a 3 cross if I again apply a 5 by 5 filter, then it has to be 5 by 5 by 6. And if I apply this filter over this input dimension, then you are going to get 10 by 10, because 14 minus 4 and 14 minus 4, there's a 10 by 10. And because it's 6 filters, then you are going to get this thing, because one filter is going to produce one feature map of size 10 by 10. And how many filters you have applied? 6 such filters. So it's going to be 5 by 5 by 6. And then you do the max pooling. So once you do the max pooling, you are going to get, so here he has applied actually 16, I'm sorry, here he has applied 16. So you are going to get 16 outputs. So here it was actually 10, here you have got 16 such things. And I guess I guess that from here what you are going to do here is that max pooling. So that becomes 5 by 5. And over this 5 by 5, over this 5 by 5, we just flatten it. So now you can understand that after flattening, it becomes 120, then 84, and then 10. 10 is actually the output. And this output was, why it was 10? Because that was being trained over a data set of handwritten digits. I guess MNIST and I guess NIST, Daksh may have talked about this MNIST, in which we have 10 characters, that is being 0 to 1, 0 to 9. So that's a classification. So anything which is being shown, LeanNet was being designed to understand that what is written inside that handwritten thing, 0 to 9. This was the first architecture. And that was very old architecture, very simple, very old architecture. In 2 minutes to 10 minutes, probably you can code maybe in the next lab. So the next session is going to be a lab session in which we are going to code all this stuff from scratch. Not from scratch, but maybe from TensorFlow in next lab. So this AlexNet, we are going to talk about this second network, and that was actually in 2012. Previous was in 1998. That was a very old network. In 2012, they have come up with the one of the best architecture, AlexNet. That is as compared to the new architecture, it's very small network. But at that point of time, and if you compare with LeanNet, it was actually a deep network. That's why they started to call this stuff as deep learning. So in AlexNet, the thing was that, let us see this architecture in detail like this. So this is actually the architecture. Let us see it. Your input is going to be 227 by 227 cross 3. This is my input size. Input size is fixed. So every network has a fixed input size. So if you wanted to take any network, this AlexNet network must be available on internet, and pre-trained AlexNet network. Pre-trained means that, so I will talk about this pre-training once I am done with this. Let me write it, pre-train.
Sir?
Yes.
Hello. So to apply AlexNet, we have to transform our input to 227 by 227 by 3, right?
Yes, that is correct.
Okay, so then only it will work.
Then only it will take input. Otherwise, you will not be able to give the input. Sometimes it may happen that you will have to interpolate and extrapolate your image to 227 by 227. Sometimes you zero pad your image. Okay. Sometimes it may also be the case that you have only 227 by 227 not an RGB image, but the grayscale image. Okay. So what we used to do is that we convert this grayscale to RGB by replicating the same thing, the same grayscale information in 3 channels. Okay. So all these things are being done just to run this AlexNet. It performs well. I mean, it's good network.
And one more thing, in the last use case, I saw one Gaussian connection somewhere was written. What was this? in the LeNet.
See, yes, LeNet, the Gaussian connection was there. That's actually a very old type of network.
Okay.
Here.
Yeah.
So this was actually the Gaussian connection at that point of time. You know what happened, that the sigmoid and other types of, if I say, last layers activations or the softmax activation. I actually have not probably talked about the softmax activation. We'll talk about this. So those things were actually not being present. So what they have done is that at last layer they do some type of Gaussian normalization.
Okay.
So as to, you know, make everything into the same level, so that at last, suppose that this value is 10 and this value is 3. So how you can say, and suppose that this value is 0.2. So you can easily say that this is that's the highest value. But you know, sometimes it may happen that things are not very far separated. Suppose that 0.5 and this is 0.55. So this Gaussian normalization helps to somehow understand that the input is belonging to which class. Now it's not being used. It's being at that point of time being done. Yes. So our network, the thing that we are right now seeing is that the AlexNet, there's a 227 by 227 by 3. And then let us understand that how to read these type of networks, and then you can easily understand the stuff. So first they apply 11 by 11 filter. So 11 by 11 filter is actually a very, very big filter. 11 by 11 means that this is my center pixel, and then you go 5 steps up, 5 steps down, 5 to my left, and 5 to my right. So if you do this much, and then it's actually a very big filter. If I say 11 by 11 filter, how many parameters are there? 121 parameters are there. And how many such filters? They have applied 96 such filters. So if you are having 11 by 11, that's a 128. In one dimension, in one filter, there are this many number of parameters. Then 96 filters are going to have this much number of parameters. It's actually a huge amount of parameters which are being there. Not only that, it's actually a very big filter. But the point is that why you are looking for a very big filter? Very big filters are several times being required, and that was again an old paper. But at that point of time, they have wanted to apply a big filter. And the reason was that if you apply a big filter, then you will be able to see big things. If you apply small filters, then you will be able to see only small things. So suppose that if I have a image like this, and there is a line like this, and if you have a filter which is a small filter like this, then you can say that there is a line, there is a line, there is a line, there is a line, there is a line. So that is why you can see it in this way. But suppose that you have a big filter, then you can easily understand that, yeah, there is not a line, there is actually something which is very well defined as a V. So sometimes you require bigger filters. So if in the downside of big filter is that it is going to have huge amount of parameters. But the good thing is that it can capture the big structures. It can capture the big structures, the thing that you are looking for, or it can see your image in a much more holistic form, bigger form. So what they have done is that they have applied 11 by 11. But the point was that initially, if you apply small filters, then you need to take too many strides. If your filter is small, then you will have to take too many steps to move in your X and too many steps to move in your right, so as to finish the image. If it is 11 by 11, if it's such a very big filter, then you can easily scan the whole image. If you can easily scan the whole image, it becomes very fast. So now you see that from 227 by 227, without applying any max spool, they have directly come up to 55 by 55. That becomes the size. It becomes very small. How it becomes very small? You just check that if I apply 11 by 11 filter over this filter, and the previous formulas are also being given. Using those formulas, you can see that 55 by 55. And how many such filters? 96 such filters. That is why you have got a depth of 96 here. And then they have applied the max pooling with a stride of 2. So if it's actually a max pooling, the size becomes half. Then you apply some type of normalization. This normalization is exactly the way we have said that the ReLU and different types of normalizations, activation functions are also being there. Then you do the convolutions again, and then you do the max pooling, then you do the normalization. So now you see that you are doing conv pool, conv. And what they have done, initially they have applied 11 by 11, then they have applied 3 by 3, then they have applied 5 by 5, 3 by 3, then 3 by 3, 3 by 3, 3 by 3. And now the problem is that and then at last pooling, and then the fully connected layers. This is the general architecture we are going to see. This is going to be our general architecture continuously throughout the time. But the point here is that it becomes very confusing when to apply 3 by 3, when to apply 5 by 5, when to apply 11 by 11, how many filters one should have to apply. So this actually at that point of time was a hit and trial type of rule, and they keep on doing their experimentation, tweaking and training these parameters in such a way so that to come up with something which performs very well over some given data sets. So what they have desired, got data set was that actually a image. This is called as the ImageNet data set. This ImageNet data set is having 1000 classes, and for each and every class they have got huge amount of images, millions of images they are having there in their data set. And this is actually a very big data set, 1000 classes. This was at this point of time, it's not that much big. We are having much more bigger data sets, but in 2012 that was actually a very big data set, 1000 different classes. So and that is why you can see that the last layer was actually 1000 neurons, they were being there. So what they have done is that they have tweaked their parameters in such a way so as to come up with the best possible hyperparameters to get the best possible results. So that was their work in 2012, and they have said, I guess, the one important thing, that as soon as you go down in your network, you are going down in your network, means your layers are increasing from here to here, then filters got increased. You apply more and more filters, apply more and more filters, and the output size keep on decreasing because you are doing filtering, because you are doing max pooling. So output size keep on decreasing and filters keep on increasing. So if you go down your network, number of filters is actually increasing, and output size is going to be decreasing. At some point of time, you assume that your size becomes very small, and you need to now open them. So that's the flattening that we used to do. So AlexNet has said that you keep on increasing the filters, and the size of filtering they have come up with sometimes 3 by 3 and 5 by 5, and very confusing. So at that point of time, that was the only possible architecture in 2012. Later in 2013, a very, very good architecture that is actually called as ZFNet, that is actually came. And this structure was not very different than the previous structure. The only difference was that they applied this, in case of this 11 by 11, they applied 7 by 7. Previously, at that point of time, 1 year back in 2012, they were not having sufficient amount of hardware to apply 7 by 7, because if you apply 7 by 7, then 7 by 7 keep on moving in its left and take good amount of time to finish the image in both of these directions. 11 by 11 moves fast. So that is why if they apply 7 by 7, it was too much time consuming. In 1 year, they have got additional hardware. Such a hardware can apply 7 by 7 as well. So they have applied this, instead of that 11 by 11, they have applied 7 by 7. And then the last conv layers, if you see that the last conv layers, this and this and this, they have applied these many filters, 384 and 256. So instead of that, they have applied more filters. So actually what happened that in a year, they have got huge amount of new hardware, and they have made a network in which they can apply more and more filters within a particular layer. just by doing that, their performance actually got far better, I mean, better than the previous network. So the game actually started in 2012, and then 13 they started to build their own networks. This network was being proposed in 2014, and this is actually a very, very good network, VGG network. And the good thing was here that starting from first to the last layer, for each and every layer, they have said that you need not to differentiate in terms of the size of the filter. You keep on, so suppose that this is my layer, and layer keep on decreasing, increasing here. Layer is increasing in this direction. Then they have said that yes, filters got incremented, and filter size, that is 3 by 3 or 5 by 5 or what, they fixed it to 3 by 3. Now that was actually the good thing. They have shown that the generalization is there. First you apply 64 filters 2 times, then you apply 2 conv layers with 128 by 128, then they applied 3 conv layers by 256 by 256. So you see, this was my input, this is my input. Given this input, they have said that first you apply first conv layer, then you apply second conv layer, then max pool, then third and fourth conv layer, then the max pool, then fifth, sixth and seventh conv layer, then max pool, 8th, 9th and 10th conv layer, then max pool, 11th, 12th and 13th layer. So now you see that the network becomes much more deeper, first of all. Second point was that they have said that instead of doing that stuff of different sizes, they have said that no, just apply 3 by 3. Everything other than this going to give you similar type of result, very similar. So just no ambiguity, just apply 3 by 3 and keep on increasing the filters. So first you apply 64, then you apply 128, then 256 and 512. Once you are done, you apply max pooling and then fully connected 1000, and then you have done the soft max. This network VGG, is it okay, understood to everyone? VGG network?
Yes.
Yes.
But I mean, what kind of like how will we know like each one, does this cover all kinds of inputs, or is it only for alphabets or numbers, or is it
No,
for
yes. So this was not actually for the alphabet and the numbers. This was actually, so the alphabet and numbers, that data was MNIST data set. All these networks are actually trained for a very complex task over the image net data set, in which we have said that it's going to have 1000 different classes. So you can here also see that the last layer is actually a 1000 dimensions. And this is going to, it has to learn a very general image representations so that it can perform well over any type of shown image, because it has to work over 1000 different classes: cat, dog, bus, train, all different types of complex classes were actually being there in this data set. Yes.
So if for example, if there is an image which is not available in this data set,
Yes.
it will try to match it to the highest probability data set in that, right?
Yes, highest probable class in our data set. Yes.
Got it.
That is
Thank you.
okay. So the good thing with this VGG network is that filter size remains to be the same, and as soon as you go into the deeper layers, you apply more and more filters. That was the outcome from this network. And till now you can see that all of these networks were good, and the only good thing was that they keep on adding more and more layers, and they started to get better and better performance. So you keep on adding more layers, you keep on getting better performance. If you have got in the previous network, you have got 10 layers, they have come up with 15 layers, then somebody come up with 20 layers and 30 layers, and at that point of time it was actually performing in that way. So they have also shown that huge amount of parameters were being there. So total parameters were actually huge. I mean, it was like millions of parameters were being there. So you can compute these parameters easily, that how many filters are there and what is the size of each filter. You just multiply, that is the thing. That suppose that it's actually suppose that it's a 3 by 3 by 3 filter. Suppose that, sorry, suppose that it's actually yes, yeah. So if it's actually a 3 by 3 filter, then how many such? 64. So this is the number of parameters. If it's a 3 by 3 by 64 filter, how many such? 64 such filters. This is the number of parameters. Max pooling doesn't require any type of parameter, so that is why no parameter. And then again doing the convolution, again you are doing this convolution, then number of filter 3 by 3 by 64 and 24 such. So this, so if you add all of them, this is the total number of filters. Huge amount of filters were being there, and huge amount of parameters are actually being there. Yes, so with these networks, we have understood a few things, that you keep on adding more layers, more convolution layers and max pooling and all, and you are going to get better results. One other thing is that down layer, as soon as you go down in your layer, apply more filters, and mostly you keep fix your filter size, and you are okay and fine with this. So after this, they have said that we have to come up with something innovative in terms of our classification networks. These are actually classification networks. So then it started to say that we actually somehow come up with different types of classification networks, and actually in between I will start to get a call. I just wanted to answer in 2 minutes, right? There is a call, important call. No? Yes sir. नहीं, this is okay. मैं आपको सर अभी आप सोएंगे, मैं आपको आधे yeah, so I was saying that you keep on adding more and more layers, then you are going to get better and better performances. The point is that now they have come up with something which is has to be something innovative and different than just adding more and more layers, because adding more and more layers, first of all, somehow have to understood in a way that adding more and more layers always is not going to be beneficial. So I'm going to leave this Google Net. I will talk about that in upcoming time, but first let us talk about this residual network that is actually called as ResNet, and it performs extremely well, and it's actually an ultra deep network. Till now we are talking about 10 to 15 or 20 or 30 layers. Now I'm going to talk about 152 layers. 152 layer network. It's a very, very deep network. And what they have shown, first of all, let us understand, is a plain image. And they have said that if you have a 20 layer, if you have a 32 layer, if you have a 44 layer, and if you have a 56 layer, I am keep on increasing my layers. And if I keep on increasing my layers, at some point of time, what has happened, that their loss is not actually coming down. Your loss with 20 layer is this, 32 layer is this, 44 layer is this, and 56 layer is actually this. So the loss is actually not getting down, even if you are adding more and more layers, and your loss is not getting down. Now this is the problem. Everyone assumes that if I add more and more layers, you are going to get better results, but this is not happening over here. And then they have said that there is some problem. Let us talk about that. But they have said that don't add more and more layer naively. You will have to understand the mechanism of adding new layers, and that is actually they have introduced. And they said that if you use our criteria of adding the layers, you see that this is our 20 layers, and then you see that your loss is going down and down. So now you can see that with more layers from here to here, your loss is actually getting down. So adding more layers, you are getting certain good, better performance. This was the thing that we are going to see right now. And what was the thing that they have introduced? Yes, so you understand the question, that what was the reason that I didn't have said that, but if we add more layers, then we are not getting performance. This is the question asked by them. Is this okay to everyone, this question?
Yeah, but can you please go
Yes.
back?
Yeah, go back. Okay, yes.
But what is the difference between the plain nets and rest nets? Oh, okay, it's a difference between two networks here and so no,
Yes, so
not.
this was actually plain net, in which you are not using the residual type of adding scheme, adding more and more layers. And this was the residual nets. They are saying that if you increase layers like this, your loss is not getting down. And if you are increasing your layers, as we have said, your loss is actually getting down. This black is actually going down. This black is for 110 layers.
Got it. Yeah.
Done? Okay.
Yeah.
Yeah, fine. So now let us understand it in a better way. Why this is here? Yes, so we are here. Yes. So the point let us understand is, the first thing that one should have to understand is that, suppose that this is my network, and suppose that it is having, say, 50 layers, and with this 50 layer you are having an input I, you are getting an output Y, and with this Y you are getting your accuracy as say 71%. Suppose that if I add one more layer, I assume that your accuracy should have to go from 71 to maybe 71.5 or something which is more than 71. It has to be, more than 71. So if it is more than 71, but what happened is that if you keep on increasing more and more layers, your accuracy is not incrementing. Second thing, that it is not even incrementing, but maybe decrementing. Is it the case? Why it is happening? And actually everyone wanted to know the answer. They got disturbed that we are adding more and more layers. Initially, if I have 12 layers, I add 13th, I get better performance. I get 14, I get even better performance. I add 20 layers, I get good performance. The 21st layer, I am not able to get, or maybe 21 is going to give me good performance. But maybe after 50th layer, maybe after 60th layer, if I add one or two more layers, my performance is not incrementing. And the point that they wanted to say is that, suppose that this is my network, and it is giving me 71 performance, 71 accuracy. I add few more layers. Suppose that these layers are not going to give me any good performance. Why my network don't understand that instead of doing anything useful, just carry on the previous output, which means that with this output, if you see that with this output, I am getting 71%. With this output, I am getting 67. So my network has to understand that I am not doing anything good, anything useful over here, So why I am doing all this stuff over here? I just here have to know and understand that what I have got here just being directly transferred to here. This is called as identity. Why this network is not able to learn the identity in the best possible way, or easily it can learn this identity. Do you appreciate this point, that learning identity is the point that network has to understand? Is this okay?
Yes, sir.
Yes, sir. Yes. So the point is that so that is what they understood, that learning identity, it's not very easy or trivial. Everyone assumed that if I give you 10 rupees, you just have to need not to do anything and just give that 10 rupees back to me. That's very easy. It is easy if you are a completely dumb person. If you are a very heavy, high and weighted parameters like this, it is not very easy directly to learn this identity very easily. Identity learning is a very different thing. Identity learning is not a different, but it's actually a very difficult thing in such type of deep networks. So what they have said is that, so let us do it in a step by step manner. and it is very easy. In fact, not a very difficult thing to see. They have done it in this way. Let us draw a diagram like this, and then I will show it to you. So they have said that, this is my layer number something, maybe layer number 121. This is layer number 122, and suppose this is layer number 123. They are saying that I wanted to add this connection. I am having this connection. This is my forward connection because all these layers are connected. I am having another connection, and this connection is actually called as the skip connection, and this is also sometimes called as the residual connection, and that is why it is called as the ResNet, residual network. And it is saying that 121, the output of my 121 layer is actually being directly fed to 123rd layer. It is already going in this direction as well, but I am also adding from top, and this will learn my identity. Suppose that this guy is not able to do anything or do something which is very good. Instead of going things directly from here, I am directly sending things from my top. So it will let my network learn the identity as well as possible. So these are actually called as sometimes identity connections as well, or the residual connections as well. And the good thing is that in between, you need not to learn something which is very trivial, because learning very trivial like passing the same thing, it is getting difficult. So I'm passing the same thing. If you have to, so here you can learn something which is better than by passing this thing. Let us assume it in again something in this way. Let's suppose that I wanted, here I know something like X. Here I wanted to learn something which is Y, and my assumption is that since something is in between, it has to be learned in such a way so that X content is always more than Y is always more than X. So what I used to learn in between is that so here I need to learn this full Y over here. If I have a connection like this, I am not learning this full Y. I need only to learn Y minus X, because X is directly being given. If X is directly being given, you need not to learn X, you need to learn. So this network, this layer has to learn something which is not Y, but that is actually the Y minus X. That is actually called as the residue that it actually need to learn. Only residue need to be learned instead of learning the full thing. So that is why it actually somehow managed that if you wanted to add more and more layers, they have shown that if you wanted to add, so if you wanted to add more and more layers, don't do it naively. If you do it naively, then probably you may not be able to, yes. So if you do it naively like this was actually their naive way, or the plane networks. If I say that the plane networks, that the plane network is actually, they apply 3 by 3, 3 by 3, 3 by 3, 3 by 3, and so on continuously, and 64, 64, 64, 64, and keep on adding, and then at some point of time 128, 128. So this is their block number 1, then the block number 2, and keep on adding that stuff. If you add more and more layers, they have seen that no, it's not going to help me and increase my performance after a particular layer. But then they have said that instead of adding them naively, let us do it in this way. I add this, I add this, I add this, and then I add this. I will talk about these dotted connections, but now you can see that these connections are actually called as residual connections. And these residual connections are also not only making our network deeper, because deeper networks can learn, but if they are not able to learn, at least they are not going to decrease the performance. Why? Because the previous layer feature is anyways being there. So if your previous layer feature was giving you a high performance, and in between you're not able to learn anything, then the previous feature is anyways with you, and you need not to worry about the performance. It's not going to be less than any previous layer feature. So that was actually the concept behind identity, or the residual learning. You can ask if you have any question about residual connections.
So this is specific to some kind of problem, or it is general problem like
It's a general problem. Yes, it's a general problem. See, what happened is that if you have more and more layers, it is just like that you say that, you have a car, and if your speed is getting high and high and high, then the time is definitely going to be reduced to reach your destination. But assume that you have got a speed of say 50 kilometers. Then if you have a car that can run in 60-kilometer speed, you can reach, slightly faster. But suppose that if you have a car which is 70 kilometers, then probably you again have got some benefits. But suppose that your car is already running on 100, and you again get a car which can run at 200, then probably, and you are running them in Indian scenario, then you will not be able to get that high performance. It's not directly scaled up. To train these high computational networks, you require also huge amount of data. And if you have more and more layers, very easily they got overfitted. And because of that, your network is not able to learn new things. So this is the problem, and they have come up with the solution of this problem by residual connections, that instead of adding plainly layers like in this plain network, you add them, okay, but with the residual connections. So that's actually the problem. And if you wanted to have more and more layers, then everyone now uses this residual type of connection.
The example you explained about the car speeds, right? Can you
Yes.
explain one more time?
Yes. The example is that suppose that you have got a car which is having, that can run on 90 speed. So you want to go from X to Y, probably you may reach very fast. When suppose that you have got another car that is of 90 speed, that can run on 90 speed, then your time can be even lesser. But suppose that you have got a car which is running at 200 kilometers per hour, and then what happen is that if it is running on 200 and you have to run it in Indian scenarios, then probably you may not be able to get the expected speeds that you are looking for. You assume that 100 kilometers and 200 kilometers, the time has to be half, but it's not happening. It is not happening because you do not have scalable roads. So here you are doing, you keep on adding more and more layers. You are making your network more and more complex. You are getting more and more parameters to need to be trained, but you do not have that much amount of data. And if that is the case, then what happens is that instead of getting higher accuracies, probably your accuracy may got stagnant or even get reduced. That's the example. And ResNet, or the residual connections, ensures that if you keep on adding more and more layers, you are allowed to add. But if you add them with these residual connections, adding them via these residual connections, then they somehow manage that whatever the time it was being required to required by your 100 kilometers car, it should not be less than probably the 200 kilometer car. It has to be somehow being scaled in that way. So what here they want to show is that with 100 layer network, if your performance is 70, then with 150 layer network, your performance should not be less than 75. It has to be at least 75 or more than that. So you add more and more layers by this residual connections. Is it still not clear? Then I can again explain.
No, but why was the name stripped there? I mean, I was thinking strip means it will strip the few of them. It was instead of wasting time there.
Correct. So it's actually skip. You can see that it's actually directly coming from here to here. So it is skipping this thing. It's skipping here, and then it is going here, and then it is going here. So suppose that in between you are not learning anything, then this is directly going from here to here to here. So that is why it is skipping in between one layer.
Oh, okay. So over the time, based on the more and more inputs, it will start learning more that how much it should skip or how much it should continue.
Yes, how much to skip and how much to add. I guess that you have got the correct thing. Yes.
Okay.
How much to skip and how much to add. Yes. So both of these things are required. Sometimes it's my my answer was that, skipping the full thing. It is not the case. You are skipping with certain thing and you are adding also. So at this point of time, at this location, you can see that it's actually being added. You are getting things from here as well as from here. So how much to skip and how much to add, carry on in the forward direction, it has to be somehow learned. Yes.
Got it. Thank you.
So this was actually a very nice and neat and clean network of residual connections, and with that they have shown that the performance got considerably increased, and with an incredibly deep network. So these networks were actually being very, very deep. So this was 152 layer network. So at that point of time, it was the deepest network, and the performance that they were getting was also very, very good. And then we, in very small amount of time, we are going to talk about another very, very useful network that was being defined. And now you can see that's actually called as Inception Net, because you can see that it's a very complex type of network. This is actually the Inception Net, very complex and very deep network, you can see. And we are going to talk about this network and the innovation. So Residual has done some type of innovation in the type of topology. So topology says that how these layers are connected. So it has said that instead of plainly connected, you can have multiple residual connections by which you are adding. We are now going to talk about another network, which is also going to talk about a special type of layer that is actually being introduced. And this layer is actually the Inception Module. So this was their Inception Module. And what is that? So let us understand that when you have an image, you keep on applying different types of filters over that. And then you say that why to apply 5 by 5 or 3 by 3 or 6 by 6, 7 by 7. You want to apply, say, one fixed 3 by 3, because in one layer you can only apply one type of filters, either 3 by 3 or 5 by 5. But suppose that if you are applying 3 by 3, which means that you will be able to see certain different types of different aspects of an image. If you apply 5 by 5, then different aspects are going to be seen. It is just that if you have a small lens, what type of things that you can see. If you have a slightly bigger lens, then what type of things that you can see. And it is going to, dependent upon the objects that you are looking for. Sometimes you wanted to see very small objects. Sometimes you wanted to see bigger objects. So it depends that what type of object you are looking for. And you say that I wanted to apply 3 by 3 filters fixed. Then some guy will say that why only 3 by 3? I wanted to apply 3 by 3 as well as 5 by 5. Why? Because I'm interested in TT ball as well as in football. In my object, when I am trying to classify, I am interested to understand that where there is a TT ball and where there is a football. And how can I differentiate? Because both of them are at different scales and both of them has to be seen by different type of lenses. So that is why Inception came. This network says that you need not to commit to a single size or the single filter size. It says that at every layer we are going to apply, multiple size filters. What it has done is actually being shown over here. This is my previous layer. This is my previous layer. This is my next layer output. But what is being done in between is that we will, so just you see that one by one convolutions. So we will talk about these one by one convolutions right now, not today, maybe in the next lecture. But assume that these one by one convolutions are very good for getting my things as fast as possible. We will talk about this one by one convolution. They make my network, these one by one convolutions make my network very efficient and very fast. Right now you assume this. Maybe in next lecture, anyways, we are going to talk about this one by one convolution. But other than that, you just see that what it has done. It has done that over any previous layer feature that we have got, I'm applying one by one convolution, fine. Then I am applying 3 by 3 convolution, fine. Then I'm applying 5 by 5 filters, and then I'm applying max pooling also. I am doing all different types of things. I'm applying 1 by 1 filter, 3 by 3 filter, 5 by 5 filter, and max pooling. I'm applying all of them simultaneously. And once I apply this, once I apply this, once I apply this, and once I apply this, I am going to get multiple different types of features. And those are actually the outputs that I'm getting. You actually get output over here. You will get outputs over here. You are getting outputs over here. Suppose that here I have applied 64 filters. Here also I have applied 64 filters and 64 filters. So you are going to get 64 outputs here, 64 outputs here, 64 outputs here, and 64 outputs, suppose that here. And if I concatenate all of them like this is my 64 plus 64 plus 64 plus 64. That is actually 256. So actually I have got a feature like this. This feature is actually called as coming out of my Inception module. And this feature is actually multi-scale feature. This is feature which is not having a single scale features. It's actually having multiple scaled feature in one layer itself. So because in your objects are not of the same size. Football is also there, TT is also there, and car is also there. So your objects are actually having a multiple scales. You need to have a tool, a layer that can look to your images at multiple scale so as to detect all of these different types of objects as well as possible. So maybe I assume that maybe in my next lecture I will start with this Google Net again, and I have to talk about this one by one and this structuring of this output, because this one by one is very, very important. So I require some time to explain this one by one, and then we will come back again to this Inception module and this network. And maybe in next lecture, first I will finish this, and hopefully with this COVID and other things, next week probably we are not in a very bad shape. I assume that we must be in a good shape. So we all are going to listen to this in our next upcoming lecture in lab. So that's going to be a lab.
So I have a question, Aditya.
Yes, please,
So,
please.
so when you have like, for example, it may be car, or it may be animal, or it may be some human being, right? So
Yes.
when it comes, even though it knows, for example, assume a dog came, and
Yes.
when it is trying to compare with, I mean, one of the set with cars,
Yes.
will it continue or will it stop doing it, because there is no point of continuing a dot with car, right? So that set, it will skip here if the data set it sees that this is going bad here, this classification.
Yes. So in this, what is happening is that, these are all my in the initial layers. All these initial layers are actually trying to find out different image representations. So probably, and those representations which are very unique, so that the my last layers can somehow see that whether there is a car, whether there is a dog. So they are trying to learn some unique and general image representation. Now what happened is that, suppose that this is my penultimate layer and this is my last layer. So here I am going to have different types of neurons, and these neurons, some of them actually fire. Maybe if there is a dog, then this and this and this, these three neurons are going to fire. Now suppose that there is a cat, maybe only this neuron will fire. For cat, maybe assume that this neuron is firing, and maybe for a car, maybe this neuron and this neuron, they actually fire. So why they are firing? Because there are some common features in cat and leopard, and because of that, few same neurons are fire and few different neurons will fire. Suppose that there is a dog and there is a mouse, dog and there is a laptop, then different types of neurons actually fire. In both of these cases, for dog maybe this and this neuron will fire, but for computer maybe this neuron and some neuron in between actually fire. So that is why we require enough number of neurons which are in between, so that they can learn out of this generalized structure. They are anyways going to be flattened in this. So these are actually generalized structure in which you are looking different types of edges and different types of visual context which is being there. Now, how to relate this visual context here, so that in the last layer you are able to see different objects, because in last layer only one neuron will be there for my cat, one neuron is only there for my dog. So if this is my cat and this neuron is high, which means that there is a cat. This neuron and this neuron is high, which means that there is a dog. And maybe this neuron and this neuron and this neuron is high, that actually says that there is a house. So it depends. So that is why the previous layers, these are actually different types of features that we are looking for. Features. And to get the best possible features, we require complex structures by which we can learn the non-trivial features which are being there. How these features are being aggregated by the upcoming layers, that is going to be learned by the fully connected networks. That is why we employ these FCs in my last layers. Is this okay? That's fine.
Yes, I think
yeah, okay. Okay,
question.
Fine. So I request you that please go through the study material to for this lecture, because I assume that those who have listened to it the first time, it's again going to take some time to digest. Maybe in the next lecture, first I will talk about this Google Net and one by one convolutions again, and then maybe some lab content is going to be there.
Sure.
Fine. Okay. Then see you.
Yeah. Thank you.
Okay. Bye bye.
One last question. Sorry.
Yes.
Before.
Yes. Please ask.
Yeah, this is Rajesh. So we have so many case studies, right? Like Google Net and all of that, and then we know that like which one is used for which case we can use. So and all these cases mainly we are referring to some of the like reading on the images, or let's say some. I think mostly the examples based on that we are looking to like get into the deeper of the image and go into the pixels of each and every pixel and reading that. So how does it will be like in normal use cases where we will implement these kind of case studies?
Yes. So as I said that we are learning currently, we are learning CNN. CNN is actually convolutional neural network, and this is only for images. This network itself is images. When we are going to talk about text, then it is going to be recurrent neural networks, RNN. So if you have wanted to work on stock market data, any time series data, that day 1, this is the thing, day 2, this is the thing, day 3, this is the thing. So if you want to work in this time series, then you require RNN type of stuff. So we will talk about this recurrent neural network once we are done with the CNNs.
Okay.
So
and also one more.
Yes.
Yeah, please carry on. Sorry.
Yeah. So like when we are going to use these case studies, is this like it is again the infrastructure wise, like does need to be like more memory and also more networks we need to have, or it can be like in a normal like let's say in a normal cloud environment we can the basic cloud services, if I take update, then we can use there also.
Yes. So the point is that suppose that if you want to do normal classification and just the forward pass, you understand only that this part is you are going. So sorry, forward pass is like this. So you are not doing back propagation. You have got the pre-processed weights. Everything is learned. you have got a new image, you just wanted to know that what is the classification that you are getting over here. That is the only forward pass. So for that, simple machines and simple cloud environment is okay. But if you wanted to train it for your network, for your own problem, then it is going to take time when you wanted to do the back propagation.
So that means train in the sense like when we are going to write our own case studies and then our own neural networks, implement all other case studies and get a new case study, then it is going to be like a new, like that normal cloud, it may not be work, right?
Even though given an Inception type or this Google Net that I'm talking about, this network is publicly available and the weights are also publicly available, trained on ImageNet dataset. You download those weights. You wanted to run that for your classification, it will run. But suppose that you have got your own dataset of 50 subjects, only 50 different classes. And over that you wanted to retrain this network, Google Net. Then for that you require training. For that training, you require GPUs.
Got it. Okay.
Yes. Yes. Somebody else was also asking.
Yes. The video classification also comes under RNN, because the last section you told it is a time based.
But it don't come in RNN either. Probably you can see that as well, but actually that requires 3D CNNs.
Okay, 3D CNN.
3D CNN. So 3D CNN at some point of time we will also try. So it's just an extension of 2D CNN. And yes, so 3D CNN will help you. So maybe we will also see in the upcoming lectures in CNN itself one day that how to design 3D CNN. It's actually very simple, exact extension of 2D CNN. In 2D, you can see that we can move in X and Y direction, right?
Yes.
3D CNN only says that I am having a 3D filter 3 by 3 by 3. Now the first 3 by 3 and the last 3 is actually in time. So now instead of only moving in X and Y, basically in horizontal and vertical direction, you also move in the Z direction, which is actually the time in such cases. So that actually becomes 3D convolution, and that can be used for video classifications. Okay, fine.
So
anyone else?
One last question.
Yes.
Sorry.
Please.
So when we said for images we have these case studies, CNN, and for test we have another test and time series, we are going to use another case studies. So let's say if when we are the text also, when we are reading, is there anywhere we are also going with the pixels and then we are going to read, or it's like I'm just getting it is that image also will be important when we are going to get into the text case studies?
So everything or these types of things are being done in which convolutional features are being computed over their CNN, RNN is applied, recurrent neural networks are applied. So first you see via convolutional layers and then you apply recurrent layers. So right now it is being happening in that way, that convolutional layers, then recurrent layers. Sometimes you're only working on text and text is written in, I wanted to go there. So it's not an image. This is actually the text encoding which is being given to you. If it's a text encoding, then you do not require any image analysis. You just apply any type of language model, and these language models are mostly recurrent neural network based models.
Okay.
So I have one example.
Just
now you explain. So what example? Suppose I want to read an image. Suppose one car is there, right? And I want to read their number plate and the person who is sitting in driving seat. And suppose one case study, you assume if number match with this person name, right? The gates will be open, right? So will it be the CNN and RNN both will be implemented in this concept?
See, for this actually the binding is very easy, because you are saying that getting the number it is difficult, getting the person is difficult, and for both of these things CNN is required. But once you know both of these things, it's fairly trivial, and you do not require any network to combine them. You just easily say that a simple type of code or matching code that you can write, by which you can find out this match that given this ID and given this number. So then it becomes a normal matching problem, which is not a CNN or RNN based.
Okay, got it. Okay.
Yeah.
So for stock markets, for those kind of things you mentioned, network type.
RNN.
Was it
Recurrent?
RNN?
Yes, the RNN, recurrent neural networks. We will talk about that.
I think that is the one which will be broader cases, right? Like for most of the data set, that will be more useful, right? I mean, I know image and this one is also useful, but this is like limited use cases. That will be the more generic use case, right?
No, generic. So that's what I'm saying, that RNN or recurrent neural networks are not being applied over images. In image, you wanted to ask two-dimensional questions. Two-dimensional filters are being applied. In a recurrent neural networks or a time series, you only apply one-dimensional questions because there are not much dimensions. You are only applying in one dimension, and it's actually for one day data is this, for the second day data is this, for the third day data is this.
So no, what I'm saying is, for example, the time series, for example, that is, you can apply the use case for starts also. You can apply for some sales of the company. So like that, that's more useful. I mean, broader use case is what I'm trying to ask.
So that depends. I mean, that depends your area. So that is why you are saying that is a broader case. Time series is video is a time series. Image time series is actually video. So image time series is video. Over that, we used to apply 3D CNNs.
Anil, the CNN can used for text and as well as images both together, but RNN can only use for text, which may not be like not most important than CNN, because the conventional you can use it anywhere, like the images, text, and everything, because it's going to read each and every pixels, and of that, and then it is recognizing what value is that. So.
No, I'm asking, like, for example, if I give day one, how the start performed over the last 30 years, like that, if you then it will be giving me some data of what is the chances of this start over the next 1 week, is it going up or going down, this kind of thing. So that use case can be applied, I mean, that network can be applied for sales of the cars company or some others. So more I'm more interested is what I'm trying to say. So
yes, I understand. I understand. That's what I'm saying, that huge amount of use cases are there for all these types of networks. So image persons actually most of the time apply CNN, and text persons or the forecasting or the time series forecasting and the prediction, they used to apply RNN or the LSTM based network. We'll talk about that. So and by the way, all these networks are actually discriminative networks. If I say classification we are doing, so they are trying to do discrimination. At some point of time, we will also going to see generative type of network. They used to generate images and data for you, and those networks are actually called as generative adversarial networks. Those are the GAN models. So we'll also talk about them as well.
Sure.
Okay, then see you.
Okay, thanks, Aditya sir.
Thanks.
Okay.
Thank you.
Okay, bye.
Bye.
Bye.